Okay, so welcome to the last lecture for CoCO this semester. Today is Friday, April 30th. The daily quiz number 25 is available on Gradescope. Please go ahead and answer that. Um, and again, this is going to be our last daily quiz. And like I mentioned before, I will be dropping a few low scores, maybe 3 or 4, but I'll drop a few low scores just to accommodate interviews, or you were sick, or there was some personal situation going on. Um, Homework 12, that's the only thing that is due for CoCO, and that's due tonight. Many of the students have already submitted it, but if you haven't, please turn that in before midnight tonight. No next homework, no studios due, so everything is already turned in. But as we move to finals week, before that, I want you guys to again make sure that you have all your Gradescope submissions in place. What I mean by that is if your partner has submitted something on your behalf, please, go ahead and check it. It doesn't take too much time for you to double check that. So make sure that you do all that verification ahead of time. And if you find any discrepancies, let me know right away. Now, we were talking about RAM and ROM. We spent some time talking about static RAM. How does each static RAM cell, how is it constructed using transistors? We looked at a 6 transistor configuration inside a static RAM cell to store 1 bit of information. We also looked at a highly dense alternative in terms of dynamic RAM, in which we could do the same job but with 1 transistor and a capacitor. Capacitor is getting charged and discharged, and you're using the transistor to give access to that capacitor voltage. So we started there, and then we moved on to a two-dimensional decoding example like this, where we were trying to read a particular cross section, right? Like particular 1 bit. So if you give an and again, we are not changing any bit here. The bit is being assigned by the diode, the location of the diode, but you could give an address over here and then read whatever is stored at that location at D0. So we looked at that particular config. This was the last thing that we did in the last class. Now, diodes tend to be very big, and they're not extremely fast in terms of their switching on and off. So a better alternative to the diodes is MOS transistors. So today's RAMs, they can be as small as 256 kilobytes, but they can be as large as maybe 4 megabytes or 8 megabytes per ROM chip. And the purpose of using ROM, again, is to store the BIOS or the startup programs for a computer, and they are stored right on the motherboard. Right? So today's architectures for ROM use MOS transistors. Another thing that we know about ROM is that it is non-volatile. So power goes off, doesn't matter. You power it back up again, and the contents will remain. Also, we are only reading the ROM in these examples. We are not writing to them. So uh, we have a decoder over here that is essentially going to be used to activate one of the word lines, right? So this decoder over here, we were calling it a row decoder in the previous examples. As you can see, that's the 3 to 8 decoder over here that we were using to essentially activate one of these 8 word lines. That was for the previous example. So if I come forward over here and say, all right, this is a ROM. What are the inputs to a ROM? An address. What are the outputs from a ROM? Data at that address. Okay, so where does the input go? Well, the address inputs go to the decoder. And based on whatever that address is in binary, one of these word lines is going to become active. So we could use a 2 to 4 decoder, we could use a 3 to 8 decoder, or we could use a bigger decoder. And the bigger decoder is going to essentially open up our options for the number of word lines to be more and more. But as you can see, each word line over here is connected to a MOS transistor. It's an NMOS transistor. So if I zoom in and take a look at how it is connected, each word line is essentially connected to the gate voltage of the NMOS transistor. The source is grounded for all of them, and the drain is actually pulled up to a high voltage through a pull-up resistor. Now, a pull-up resistor usage is not very ideal, just because if there is current flow through the transistor, it is also going to flow through the resistor, which means that it is going to be dissipating some power. So in terms of energy efficiency, it's not the best option, which is the reason why we talked about using PMOS transistors in the pull-up network. Right now we are just showing that resistors are there in the pull-up network, but it's not the best way to do things. Instead, if you were to use um, PMOS transistors in the pull-up network to go to VDD, that would save you a lot of energy. So in terms of energy efficiency, that would be better. And we'll take a look at some examples in the NOR-based and the NAND-based ROM architectures, which do the same job. But in general, we are looking at NMOS transistors. They are present at some locations and they are not present at some other locations. Now, earlier we said, if you guys remember from earlier, this example, wherever the diode was present, it was as if there was a 1 in the corresponding truth table, right? And wherever the diode was absent, it was like there was a 0 in the corresponding truth table. And the truth table I'm referring to is the one for this particular logic in ROM example, where the zeros were over here first, and then there was a 1 over there. So this was a 2 to 4 decoder with active low outputs and active high outputs. So wherever there is a diode, there is a 1, right? And that will be the case if you use the output inverting buffers. So you would have to use output inverting buffers so that that is accomplished. Wherever the diode is present, there is a 1 in the corresponding truth table. Without the inverting buffers, you would get exactly the opposite, flipped version of the data that is stored at any address. So we would want that similar thing to transition to a MOS transistor based architecture, where the presence of the transistor should be equivalent to making it into a 1, and absence of the transistor should be equivalent to storing a 0 there at that particular location. And for that to happen, again, we may or may not need to invert the outputs over here. So data to inverting output buffers. In some cases, you do need to invert them, but in some other cases, for example, if it was a NAND-based architecture, you would not need to invert the output buffers. So what is happening here? Whatever you give at the address input, it is being decoded, and the decoder is going to take the responsibility of making sure that only one word line is active. All these are word lines, right? So let me highlight them over here. These are all word lines. And what are these? Anyone? If those are word lines, what are these? Bit lines, right? So one is word line, WL, the other is bit lines. That's right. Um, Andrew says, doesn't it make it active low? Yeah. So the decoder, depending on what type of decoder it is, the outputs are going to be active, right? And then if there is if this guy is active, then, and if it is high, for example, if it is high, then the transistor is going to be on. If the transistor is going to be on, the way we have shown here, the example over here, that particular bit is going to read a 0 because of that. Yes, so they are going to be active low bit lines because of when the transistor is on, it is going to be pulled low, right? That's when there is a connection between the drain and the source terminals. That happens when the gate voltage is enough to turn on the transistor. But we put a transistor there and we read a 0. That's exactly the reason why we would need inverting buffers for that particular configuration. You see that? Otherwise, we wouldn't. So we will take a look at two different types of architectures we can have here. We can have a NOR-based ROM and a NAND-based ROM, where we can connect these transistors in a NOR configuration and a NAND configuration and be able to store information. We'll take a look at those things. We'll start with NOR-based ROM here. So the first thing that I would like to point out is, where is all of this going, right? So you see on the left here, we have word lines indicated by WL, and on the bottom here, we have bit lines indicated by BL. So where is this architecture going? Well, if I scroll back over here, that is essentially this part, right? So it's not the decoder. The decoder is not included there. So we are assuming that some address has been given that has been decoded. And what do we do with the word lines? Well, the word lines will need to be the word lines will need to be connected to some transistor configuration, and the outputs are going to be bit lines. So that's exactly what we are showing here, right? So word lines are over here, bit lines are over here. So we are not essentially, there is a decoder over here, which is essentially generating those word lines as the output. It's taking in an address input and giving out the word lines, making sure that only one word line can be active at any given time. But that's not being shown here. All right, next, let us talk about why this guy is called a NOR-based ROM. So you guys have seen a NOR gate construction using transistors. What did you guys remember? Do you guys remember anything from there? When we made a 2-input NOR gate, for example, using CMOS transistors, how was the configuration in the pull-down network? Were transistors in parallel? Were transistors parallel? That's right. So NOR is this or this, right? So alternative paths. Of course, that means parallel. So we would want our pull down network to be NMOS transistors that are in parallel. And that's exactly what we have over here. All these are going to be in parallel with each other. And I want to point out a few things that might be difficult to read from there. So if you see this line, that is ground. And this line over here is also ground. Okay, so let me highlight that a little bit, maybe with pink. So this is ground, and this is also ground. So the fact that the NMOS transistors are effectively in parallel, that's why this structure is called a NOR-based structure. What about the pull-up devices? Where are they? Well, all the pull-up devices or your PMOS transistors, there are 4 of them over here. They are all on, right? Because their gate voltages have been connected or hardwired to ground. They have been forced to be on. So all these guys are on already. So that means that they have already been pulled up to whatever the VDD is. What is the point of having them? Exactly the same thing as avoiding the pull-up resistor. Remember, we need a pull-up resistor to be held up to high. If I was using a resistor, then every time my transistor is on and there is current flow, it is current passing through that resistor, which is essentially going to be absorbing power. I do not want to use the resistor, right? Which is exactly why we did not construct our logic functions using NMOS transistors and a pull-up resistor. We in fact did it in a complementary fashion with CMOS, where pull-down network was NMOS and pull-up network was PMOS. So that is huge energy savings. That's the reason. We could have used pull-up resistor, but that is yeah, I mean, if it was on, why can't you just get rid of the transistor? We want this. So here, where is this going? This is going in the ROM, right? So this may be programmable ROM or it might be fixed ROM. Right now, in today's architectures, these are programmable electrically, and you can reprogram them many times. So how are you doing that? Using logic cells. Logic cells can be turned into on and off very quickly. That's why you're using transistors as opposed to hardwiring them. All right, next, let's talk about the size of this ROM. What do you guys think in terms of size of this ROM? 16 by 4. Okay, so that's one answer here, 16 by 4. Do others agree with 16 by 4, or what is happening here? So 4 is correct. Over here, 4 is correct because they are 4-bit lines, right? So there are 4-bit lines, BL0, BL1, BL2, BL3. That's 4-bit lines. So that is correct. But is this correct? 16. 4 by 4. That's right. Why is this 4? This is going to be 4, right? The reason is, if I go back, we are not talking about address inputs. We are actually talking about the word lines. You guys see that? So if this is 4 inputs, that would give you 16 word lines, right? You see that? So if this was 4, that would have been 16. But that's not the case. We only have 4 word lines. So the number of address inputs in our example is simply 2, right? So it's becoming 2 to 4. So the number of word lines are essentially going to be over here, right? So you can say number of word lines, and over here number of bit lines. So it's going to be 4 by 4 because there is no decoder shown over here. Okay, so let's talk about the number of address inputs. So size is 4 by 4. We talked about that. So to complete that conversation, we can also ask the question, number of address inputs. Address bits, number of address bits. How many are there? 2, right? So there are two address bits. That's right, 2 address bits that are getting decoded as 4 word lines, and at the output of this ROM, you have 4 bit lines. So you give me a 2-bit address, and I will give you a 4-bit data that is stored at that address. That's exactly how this NOR-based ROM is going to function. But in terms of size, we are going to not include 2, but we are going to include 2 raised to 2, right? And then by 4 because of the bit lines. All right, let's, okay, so I can write this over here because that is going to create confusion. Over here, maybe I can write that. So from here to here, we are going from here to here because of 2 raised to 2. All right, so we talked about that. All right, next, the way the NOR-based ROM works is with word lines being active high. So this is sort of a given. Word lines are active high in this case. So all these word lines, they are WL0, 1, 2, and 3. All these are active high, which essentially means the decoder has active high outputs. Let's go back. Now, to understand this better, what we'll do is we'll answer this particular question. What is stored at each address location? Each address location. That's what we'll try to answer with this example. And hopefully we can understand it while we do this. If the number of address bits are 2, then how many different address locations will I have? 4. Absolutely right. In every case, in every one of those 4 locations, it is going to be one word line being active at that particular point, right? So let us make a table here for finding out what is stored at each of those 4 locations. So what I'll do is I will go in here and say this is my word lines expressed in hex, and I'm also going to find out what is my bit line stored in hex. That's the table that I want to fill out, right? So even though the number of address bits are 2, I'm only going to have active, inactive, followed by active, inactive, followed by active, inactive, followed by active, inactive, right? So only 4 cases. So let's talk about the first one. So for the first one, I'm going to make WL0, the least significant word line, as active. So I'm going to make this one and the rest of them as 0, inactive, right? And that, of course, is going to translate to our table over here in hex as what? 0, 0, 0, 1. In hex, 1. That's right. 1. That's in hex already. All right. So at word lines 0 being active, that corresponds to maybe address input 0, 0, right? Maybe address 0, 0. What is going to be our bit lines, corresponding bit lines? So what we do here is now zoom in, and now we start noticing where is that word line connected. So each of these transistors is a NMOS transistor. And what we know about NMOS transistor is that if you want to turn it on, then you will have to give it a gate voltage with respect to source to be above a certain threshold, right? So you have to give it a high gate voltage with respect to source. That will turn on the NMOS transistor. So word line 0 is connected to this particular NMOS transistor, and word line 1 is connected to this guy and this guy, word line 2 is connected to this guy and this guy, and nothing is connected to word line 3. So which transistor in this case in the pull down network is going to be on? Can I say that this transistor is going to be on and everything else is going to be off? Can I say that? So what that means is this guy is going to be on, everything else is going to be off, because only this gate voltage is getting a high from word line 0. All right, so what does that mean for BL0, BL1, BL2, BL3? Well, bit line 0, as you can see here, well, no path to ground there, and it is connected to high. So bit line 0 is going to be 1. What about bit line 1? Cannot go to ground from here. Oh, I can go to ground from here. 0, that's right. How about bit line 2? Oh, no transistors is going to be 1, right? How about bit line 3? Bit line 2 is going to be 1, right? Because there is no path to ground. There is only a path to VDD. How about bit line 3? No path to ground from here, no path to ground from here. So it is going to be high. There it is. So in other words, the presence of the transistor is essentially ensuring whether you go to ground or not, right? So only because this particular transistor was on, there was a way for bit line 1 to get grounded. Everything else did not have a way to go to ground. They were only connected to high. Okay, so now let us see what is stored in BL. What is going to be the corresponding entry for the bit line here? D is absolutely right. So I can say this is going to be D in hex, of course. So that means that it is what 1101. You guys see that? All right. Um, Next, let's talk about the next case here, which is I'm going to erase all of this, and I'm going to erase all of this. I'm going to also erase all of this and go to the next possibility, which is 0. This guy is active, 0, 0. Only one word line 1 is active. In this case, this transistor is on, this transistor is on, and everything else is off. So what can I say about bit line 0? Bit line 0 has a path to ground, 0. Bit line 1 doesn't have a path, so 1. Bit line 2 always going to be 1. Bit line 3 has a path to ground, so 0. 0, 1, 1, 0 is absolutely right. And in hex, what is that going to be? Okay, so first of all, in the table, word line is going to be what? 0, 0, 1, 0. So that's 2. And for the bit line, it is 0, 1, 1, 0. So 6. Excellent. Let's do the next one. Inactive, inactive, active, inactive. So off, 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 on, done. Bit line 0, 1, 0, 1 always, and 1. Guys agree with that? No, that's last one is not 0. Last one is 0 because there is a path to ground. There is a path to ground. All right, so 1, 0, 1, 0. So what is 1, 0, 1, 0 going to be? It's not going to be A, it is going to be 5. And the address is what? 0, 1, 0, 0. So that's 4. So hex is 4, and what is stored at that particular location? 5. All right, let's do the last one too. Quickly, and done. The last one is going to be active, everybody else is inactive. The transistors that are on are none. Everything is off. So that means that everybody is going to be at a 1. 1, 1, 1, 1. That's right. So at location 8, 8 is corresponding to the hexadecimal value of the word lines. We have F stored. You guys see that? So, you know, address 0, 0, we have D stored. Address 0, 1, 6. Address 1, 0, 5. Address 1, 1, F. So we have got 4 address locations at which we have got a 4-bit value stored. Next, do you need output inverting buffers or you don't? So the question is, do you need output inverting buffers in this case or you don't? Do we need output inverting buffers? Doesn't it depend on what you want or need? Well, here, what you really want is presence of a transistor, store a 1. Absence of a transistor, store a 0. Now, take a look at the example that we were just doing at the end. When you did not have any transistor, you were actually storing 4 ones, right? But if you had a transistor, output inverting buffer, then you would exactly store based on presence or absence of a transistor, you would store a 1 and a 0 respectively. So in this case, we would need output inverting buffers to get that, right? See, no transistor, you are storing 4 ones. But if you inverted all of those things, you would get 0, 0, 0, 0 instead. So wherever there is a transistor present, then can translate into 1 being stored at that location. You guys see that? All right, there is one more question that I want to answer here, which is this one-dimensional decoding or is this two-dimensional decoding? 1D or 2D? One-dimensional decoding is absolutely correct. We are only doing row decoding here. If we did two-dimensional, then we would only be reading 1 bit. We are right now able to read 2 bits. So we are only doing row decoding in this case. The one-dimensional decoding is absolutely correct. All right, questions about this? What if we swapped out all NMOS and PMOS and PMOS with NMOS? Yeah, now you're that's right. And that's exactly what will get you to one of the homework problems. So one of the homework problems is exactly about that. Yes. So I guess this is a pretty big hint for that now. Nice. All right. We have one more architecture to look at, which is a NAND-based ROM. And we can answer the sort of the same questions here. We can take a look at whether it is one-dimensional, two-dimensional. We can talk about the size of the ROM. We can talk about what is stored at each location. But the first thing that I want to point out is, why is this called NAND? Well, it is called NAND because your pull-down network consists of NMOS transistors that are in series, one after the other, exactly the same way as we constructed NAND gates using CMOS transistors. A few things have changed. One, our bit lines are now connected to the gate terminals of each of those NMOS transistors. So the bit lines are over here. Similar to the previous example, all your PMOS transistors are already on. They're already conducting. So if you did not do anything, all the bit lines would read 1, right? So all the bit lines would be reading 1 because of that, if you did not have a way to go to ground, depending on the transistors. What is the size of this ROM? 4 by 4 again. Same way, same as before. Number of word lines are 4, number of bit lines are 4, so 4 by 4. Done. Now let's do the one-dimensional or two-dimensional. Is it one-dimensional decoding or two-dimensional decoding? 1D again, because we are only doing rows and we are getting 4 bits at that particular memory location as opposed to 1. So one dimensional. Okay, we are done with that. Now let's talk about the table. Now for the table, the one thing that we need to note before we start filling out this table is the fact that word lines are now going to be active low. So word lines are active low now. So the decoder outputs are going to be active low, which means that you can use some of the standard decoders that we know of from the course. So word line over here, WL in hex, and then BL in hex. That's what we want to find out. At the end, we will try to answer whether we will need inverting buffers or not. So what is the first case going to be? Well, word line 0 may be active and all the others may be inactive. Will have to be, right? Only one of them can be active at any given time. So word line 0 is active, everybody else is inactive. In this case, which NMOS transistor is on? Well, everybody is on except for this guy, which means if you look at bit line 0, it is connected to ground. Bit line 1, not connected to ground. Bit line 2, connected to ground. Bit line 3, connected to ground. So what you're reading there is 0, 1, 0, 0. What would that equal in hex? High to low, right? 3 to 0. 0, 0, 1, 0. See that 0, 0, 1, 0 would be 2. That's right. And I suppose I need to also do the word line in hex. Word line in hex is going to be 1110. E. Excellent. Okay, so next. My next case is going to be active, everybody else is inactive, on, off, on, done. So in this case, bit line 0 is going to be 1, bit line 1 connected to ground 0, bit line 2 connected to ground, bit line 3 not connected to ground 1001. What is the address in word line? 1101 will give me D. 1001 will give me 9. Next, erase, erase, done. Next line active. Word line 2 active, everybody else inactive. Now on, off, done. So bit line 0 going to be ground. Bit line 1, 1. Bit line 2 always ground. Bit line 3, 1. So I've got 1010 in this case. 1010 is A. What is the address? 101011. What is that? It is B. Next, last one. Word line 3 active, everybody else inactive. Transistors that are on, all of them are going to be on. Now, what do you have in terms of bit lines? 0, 0, 0, and 0. So at address location 0, 1, 1, so that's 7. What is stored? 0 is stored. So now let's ask the question. Do you need inverting buffers? Do you need inverting? No, you see, when you did not have, so when you wanted to store 4 zeros, you did not put a transistor there. When you wanted to store A, you put 1010, right? You put a transistor wherever you wanted to store a 1. So now you don't need a inverting buffer, right? No need of inverting buffers. All right, so we talked about one-dimensional, I think we have talked about everything over here. All right, questions in this case. NAND and NOR-based ROM structures. Talked about size, talked about decoding, talked about how do you do that, right? Now, just for the sake of completeness, we can say address bits were still 2, right? So if address bits were still 2, we could do 0, 0 is mapped to that, 0, 1 is mapped to that, 1, 0 is mapped to that, 1, 1 is mapped to that, right? So you give me a 2-bit address and I will tell you a 4-bit data that is stored at that address. That's how this ROM is working. All right, I'm going to stop recording for the memory lecture.